Ken Butler is Senior Director of Business Development in the Adventist Cloud Solutions Data Analytics Platform Group at Adventist. Prior to that, he's worked more than 36 years at Texas Instruments in DFT and test generation, semiconductor reliability, analytic product and test engineering, and data analytics. He has a BS from Oklahoma State and a MS and PhD from University of Texas at Austin, all in electrical engineering. Welcome, Ken.
Thank you, Ira. Appreciate the introduction and appreciate the MEPTEC community for the opportunity to come in and give this presentation. I'd like to acknowledge my co-author, Keith Schaub. He's the Vice President of Technology and Strategy also at Advantest. I really enjoyed Ron's talk. I'm going to talk about test too, but perhaps Ron's emphasis was a little bit more closer to the design space. And I'm going to get a little further to the right and talk a little bit more about how this AI works when you're using these ideas in production. So analytics and test operations is not a new thing. I mean, we have a history, we in this industry have a history of analyzing test data and making product decisions for more than 30 years. And I'm going to give you some examples here coming up in a moment. What's changing, what's different now is that we're moving, of course, to increasingly smaller geometries, advanced packaging technologies, and chiplet-based designs. And that's driving us to sort of change the nature of the type of analytics that we do, both in terms of the software and the hardware infrastructure. I'm going to talk about both of those components. The resolution of the decision has changed over this period of time. In the early days, it might be an entire lot or a wafer. Then we move to making a decision about of the disposition that we're going to treat as a zone in the wafer, a region in the wafer, eventually the die, and now even we're talking about doing things on a sub-die basis. So for a large complex SoC type device or whatever, you might be making decisions about what goes on in certain regions inside that die. So we're driving to smaller and smaller fractions of the overall production that we do these decisions with. So that's driving us towards the need of increasingly complex and more powerful analytics and compute infrastructure. So this is just an example from my own personal experience of how we've seen the evolution of test outliers. So outlier analysis, materials running in production, you're going to analyze the data and you're going to declare some devices to be outliers or different from the norm. How do we go about doing that? And again, we've been doing this for a long time. It's an industry. Early and mid 90s, we might make a decision to disposition an entire lot. We might be looking at simple metrics like probe yield. And we saw that move from a lot disposition to a wafer disposition using probe yield, and then eventually simple distribution analytics like Tukey analysis, where you just are plotting the distribution, cutting off the tails of the distribution and doing it that way. And then we move to wafer spatial rules, and perhaps by die dispositions, towards the end of the 90s. In the early 2000s, my experience was that we were moving to within die delta IDDQ and Vmin, minimum voltage type measurements. You might do a stress test and you would measure IDDQ or Vmin before and after the stress, and then you would run some analytics to look for movement of those particular metrics, and that would give you an outlier declaration, and that was done on a by die basis. Then we moved to sort of zonal Tukey analysis, and again using the Tukey distribution, but now you're applying on a smaller region and maybe different types of measurements that we're doing. In the mid to late 2000s, I had the great experience to work with folks at Portland State University, and there were other places doing a similar kind of approach where we're using this thing called location averaging. Location averaging is a neighborhood type disposition strategy where you can analyze a die within a certain area on the wafer and look for differences with more complex analytics than any of the things that we were doing here above, and then make a by die disposition in terms of outlier status. And then since then, the location averaging stuff, at least that I was experienced with, was all univariate in nature. But since then, people are moving to multivariate statistics, to machine learning and AI models, and also real-time compute infrastructure, because you want to be able to apply this technology not just in end of wafer, but perhaps maybe in a final test context where you want to be able to make the decision right then and there as you're testing the die. So as we drive down this technology curve, you know, the analytics, the compute infrastructure that we have to bring to bear becomes increasingly more complex. You want to be able to make the right decision with a minimal amount of overkill, and essentially customize the test solution on a die-by-die type basis. So compared to some of the other talks that we've seen over the course of these 2 days, I would say that we're probably, at least from a production test viewpoint, we're still kind of in the early days of our journey with AI and test. We have to do some things to build out infrastructure to be able to support real-time inferencing, and I'm going to talk about that here in the coming slides. We need to create partnerships and libraries of applications. You know, a lot of folks out there in the industry have big data science teams, and they can go off and do their own analytics development, and we see that with some of the folks that we're working with and talking to. But there are also perhaps other folks where they need a little bit of help in this space, and so kind of building up those partnerships to be able to bring to bear, you know, more complex analytics is a useful thing to do. We're seeing a proliferation of on-die sensors. On-die sensors are, again, not a new thing, but we see more and more people being able to use those, and that enriches the data set that you're going to be able to use for your analytics. So you're already collecting probably a lot of parametric data that can feed the models that you're using to do all this inferencing. But the on-die sensors provides an even better and more richer source of data. And that's particularly important for things like advanced packaged type products, heterogeneous integration, you know, chiplet-based designs, you know, where your lack of observability hampers your ability to do good analytics, and on-die sensors is going to help solve that problem for us. And besides just all of these things that are oriented towards the production test part of the equation, we're going to see a proliferation over time of AI tools that are going to aid in the test program development process. And I'll have a few slides at the end of the presentation to talk about that as well. So it's going to impact the overall process, but I would say in my mind, it's from where I stand, we're still kind of in early days for a lot of this. So I talked a little bit about building out the infrastructure, and so I'll give you a viewpoint, you know, not to kind of talk about a particular thing that we're doing at Advantest, but just to give you an idea of the infrastructure that we need to put in place in order to be able to develop, manage, deploy, and utilize advanced analytics as part of the production test process. And also in product development and other spaces, but I'll probably kind of focus more on production tests. What we call this real-time data infrastructure, and it has multiple elements. First off, you have to have a cloud-based infrastructure in order to be able to maintain your analytics. In our case, we call it the container hub. The idea is that you're developing advanced analytics, probably not in the same language that is used for the test platform. You containerize that so that it's easily transportable, and you can move it around from one test insertion to the next fairly easily. And this is, you need a place to kind of house that library of these algorithms that you're going to apply as part of your overall test operation. Then you're probably going to need some sort of infrastructure on the test floor. We call this the unified server, but the idea is basically that you might have these applications that are sitting in a cloud registry, and you're going to mirror a local copy if you're an IDM, it's at your own facility. It may be remotely located from headquarters, or if you're a fabless type company, maybe you have an OSAT partner or a foundry partner, and you have a local copy. You want to maintain it here for reasons of network reliability and security. You don't want all of your test cells talking to the outside world. That's a tremendous security risk. Most third-party manufacturing partners would push back on that. So you need some sort of a local resident capability. And in this case, you can also use it for things like caching data and moving it around from the test floor to remote locations if it needs to go there, so that you can have a floor-based infrastructure that can provide, you know, multiple of these services. And then finally, if you're going to run, you know, advanced analytics, you know, these things are compute intensive. You know, they may take a lot of CPU time. And I talked about real-time inferencing, where you want to make the decision as you're testing the die. So you need some sort of a heavy-duty compute platform that and enables you to be able to do that. And so we have this thing that we call ACS Edge, where you have it's controller that is managing the overall test process. And so the as you know, data is moving back and forth between the host controller and the edge compute, because again, you're going to send data over as it's being collected. You're going to run some inferencing type activities on this server and then send it back to the host controller to make some disposition in the die. Rebin the device, change test content, declare it an outlier. There's a lot of different things that you can do here. And then finally, there's one more element. It's a software component that is basically an agent that sits onside the test on the host controller on the tester, that is essentially the traffic cop that is handling all of the data communications between the test cell and the edge compute, between the test cell and the floor server to deploy analytics or bring in feed forward data, or do a variety of those kind of other applications, or send data out if you have a remote database, a cloud-based database that you're using to collect all your test results and do analysis of those, as operations are running along to look for things going on. So, and then finally, I mentioned this thing about, being able to bring in third-party analytics, so we have created a partnership where we're working with a number of different analytics providers to be able to provide applications that are containerized and ready to drop into this infrastructure. So if you haven't created your analytics on your own, which a lot of people are doing, then you have an option in terms of being able to go off and procure those from somebody else to bring to bear, and have something that is essentially ready-made for this kind of application. What kinds of use cases? So the interesting piece, what are people really wanting to do more in a production test context here? And as we talk to people and see where their interests lie, it seems like there's a really burgeoning list of all kinds of things that people want to do with advanced analytics. I've got a long list here. There's no way I would have time to go through all of this in a relatively short presentation, but maybe I might highlight a few things that seem to be recurring themes that come up quite a bit. I'll start at the bottom here with this idea of search time reduction. So for minimum voltage, maximum frequency, trim tests, those kinds of things, you tend to set a lower limit and an upper limit for your search limits, and then you're going to search across there in order to be able to find your minimum voltage for this particular device. And those limits are set based on a process split, and they may be fairly wide. But if you have analytics that you can bring to bear, that you can process with AI or ML type techniques that are basically telling you where this die lies on the process spectrum, perhaps fed forward from an earlier insertion and or perhaps combined with what you're doing at the current insertion, then you can use that kind of an inference to be able to narrow the search limits and be able to speed up that test. And we see a lot of people that are very interested in applications like this, and there are already some folks doing it in production and seeing some fairly significant benefit in terms of being able to reduce the search time for these kinds of test time intensive type tests. Shift left is another kind of thing that people are very interested in, and the idea here is that perhaps I have a very expensive test insertion at some point downstream, and or I have a high package cost. Say if we're talking about final test and I've packaged the device and maybe my package cost is fairly expensive. And if my yield at that point is not where I want it to be, then I can use analytics earlier insertions to be able to try to predict which devices are likely to fail at the later insertion by doing analysis, running analysis at an earlier insertion, and then downgrade or scrap those die in order to optimize downstream test insertions, raise the yield, and lower the costs overall. So this is another thing that people are very interested in, and people are working on analytics to be able to solve that kind of problem. Adaptive test time reduction is another one, and we've been hearing about this for years. Again, very simply, you're adding or removing test content. Skip test is kind of a popular thing for test time reduction purposes, but you might also want to add test content for yield improvement. If I have a multi-tiered device and it's not going to pass bin 1 criteria, but maybe it's a bin 2, if I add some additional content in order to be able to look at it from that perspective, then people are looking at analytics to try to make those decisions. Again, you want to be able to do that in real time. As you're testing the die, maybe I'm going to steer the test content in one direction or another, either lower test cost, improve yield, or whatever. And then finally, there's kind of a pair of things that I kind of go together in my mind in many cases. This idea in the context of chiplet designs of smart pairing. So the classic example is a processor die with a stack of high bandwidth memory on top of it. And perhaps I'm interested in both high performance in some applications and low power in others. And I want to be able to match the content and be able to classify die as they're coming through the test operation in two or more classes to be able to say, I'm going to cluster the parts, put them into those classes, and then downstream as I'm doing pick and place and packaging and those type of operations, assembly, then I'm going to put them together in such a way that I maximize the yield for multiple streams of data. Similar kind of thing for power reduction. There's a lot of applications, of course, mobile applications we all know about, but also data center type applications where everybody's trying to lower their power footprint, their carbon footprint. So people are interested in being able to classify devices and take streams of material and move it different directions based on these kinds of goals. So those are just a few examples of the kinds of things. I've got a few other things on here, but if you're interested in more, always would be happy to talk to you later on after the talk. This is just one example where you hear the expression "eat your own dog food." So we've been trying to apply some of these technologies in our own devices. We have an ASIC device that one of several that runs inside of our test equipment and our instrumentation. And in this particular instance, it has a very expensive package cost and final test cost. And the package yield at test was less than was desired. And we were looking at, well, can we take some of these ideas that we've been exploring and develop the analytics to be able to say, can we predict final test failures looking at wafer sort data? So this is kind of the shift left application that I talked about earlier. And we've had some fairly good results here where we can, in this one specific instance, talk about finding 36% of final test failures at wafer sort at a fairly modest amount of overkill rate. Overkill is the amount of devices they would otherwise pass, but you're declaring as a suspect part at the earlier insertion. And the important point to make here is that depending on your sensitivity to the overkill rate versus the effectiveness of detecting things upstream, you can adjust the model parameters and the performance to be able to steer that outcome wherever you want it to be. So if you're very sensitive to overkill, you want to minimize that, and you're willing to live with a little bit lower of a capture rate at the earlier insertion, then you can steer it one way. If it's the other way around where you want to capture as many as possible earlier and you're willing to live with a bit more overkill, then these are things that can be adjusted in the model. And we were able to move our final test yield in this example, up above 95%. There was a presentation that was done last year at the Advantest Voice Conference that talked about this. So it was an interesting piece of work where we're trying to take these technologies and bring it to bear in our own operations. This is an entirely different example than some of the ones that we talked about. And the idea here we refer to as adaptive probe cleaning. So when you're doing a wafer probe operation, by default, what you would typically do is the probe needles, as you're probing a device, are going to become dirty and they're going to need a cleaning operation. And typically what you'll do is you'll have a fixed schedule, or every so often you will go off and you will do a probe cleaning basically on that fixed schedule, regardless of what it says what it really needs. And that's a problem in terms of efficiency. It's a problem in terms of throughput, because your probe needles don't always necessarily need it at exactly that number of touchdowns. And a more desirable way to handle this situation would be to let the prober and the test cell tell you when the probe card needs to have a cleaning operation. So, we developed some analytics, and it's a kind of a learning operation where we're measuring metrics that are coming off of the test cell, and you run the probe cell on a new lot for a while, or a new wafer for a while, and you kind of look at what normal looks like, kind of create your baseline. And then from there, you're starting to monitor these signals to say, when do I see an instance where I think that a cleaning operation is necessary? And only when you need that do you go offline to do the cleaning step before you come back and continue probing. And we see folks kind of very interested in this kind of an idea. If you're doing a wafer probe operation, if you're in a foundry, you can kind of get double-digit percentages types decrease in the number of total cleanings that you have to do over a particular run of material. So it's a useful concept, and the underlying technology is the learning methodology that's used to determine what good looks like, and when when bad starts to happen so that you can intervene and do a cleaning just when you need it. Finally, I mentioned that I would talk a little bit about generative AI for test program generation. And this is a talk that my co-author, Keith Schaub, gave at Semicon West at the Test Vision Symposium last year. It was just kind of a fun thing and not really getting too much into the heavy duty idea of what exactly you can achieve with this, but more kind of playing around with the technology. So he was looking at an instance where he was prompting ChatGPT-4 to generate test code for a power amplifier adjacent channel power ratio, ACPR test. The response that came back, and this was, the ChatGPT technology has improved a lot since Keith was playing around with this a while ago, but it came back and saying, well, I'm not really trained on a library of test code. And that's not a surprise because a lot of test code would be considered proprietary. And in the early days of ChatGPT technology, it probably didn't have access to anything like that. So it's saying, what I can do here, it's saying is fairly limited. Keith would go back and say, okay, I understand that, but go ahead and do it anyway. And the interesting thing is what comes back is a fairly good understanding of what an ACPR test would look like in terms of overall structure, what the sequence of events is. It could get it to provide, what's the initial tester setup that you have to do in order to initiate the test, how to actually apply the test, collect the statistics, and then, a step that you're going to need to do the computation at the end to determine pass or failure. So even with a limited access to, the underlying training data that would allow it to do a really good job of creating this kind of a test or any other test. This is just done as an exemplar. It does a pretty good job of answering the question. Imagine how well it could do if it was trained properly. If it had the right data under its belt in order to be able to do a more thorough and detailed creation of the test content that you're looking for, then you would get a much better outcome, and perhaps this speeds up the overall test development process. And therein lies the challenge. So how do we train while protecting important test IP? Because most people are going to value their test IP, not necessarily want to do it. So we have to set up the right guardrails around the training and utilization processes so that you can apply this technology in accelerating, the overall process of developing test programs. So this is just kind of a fun exercise to say what if and where is it going. But it's clear that this kind of technology is going to be brought to bear, just like we already seeing it being done in the software development process. And there was a talk, I think it was the first talk yesterday, that talked about this kind of technology. And this is just kind of the test program development specific implementation of that kind of a technology. So this is definitely where things are going. So for AI and test, in my mind, the sky's the limit. I think we've heard several of the speakers talk about that over the last 2 days. There's possible applications at every test insertion. I showed you some examples a few slides ago. I think it's clear to me that LLMs, large language models, are going to be brought to bear to aid with the program development piece. There's lots and lots of interesting use cases. Every time you sit down with somebody in the industry, we learn about new things that people want to do. It benefits not only the products. I talked a lot about, outlier analysis and speeding up test content and that kind of things, but also the infrastructure. There's a whole space here where you can talk about predictive maintenance, being able to essentially know when the test cell has issues. Adaptive probe cleaning is one specific instance of that, but there are many others that would also fall into that realm. And we're only limited by our creativity and the kinds of things that we can come up with in order to be able to apply this technology. And Ron hinted at this at his talk. Is AI going to take my job? And there was a famous quote that probably most folks have heard by now from Jensen Huang, the CEO at NVIDIA, where he said, AI is not going to take your job. Somebody that's using AI will. Perhaps it's a bit of an extreme approach, but the point is here that we all need to kind of embrace this technology. It's clear there's a lot of advantages and benefits that it brings. And the more that we can learn about it and apply the technology in the right way, the more effective that we're going to be in our jobs. And as Ron said, the more that we can demand of ourselves in terms of trying to increase our overall output and accelerate this overall process. With that, I'll stop for questions, and thank you very much again for the opportunity to speak today.
Thank you, Ken. So let's, yeah, I just launched the poll, so if people would give Ken some feedback and put your questions in the Q&A tool, that would be appreciated. That's really interesting on a number of levels, but looking at your cloud solution, I mean, it's built around container technology, which is probably, well, it's probably not very prevalent in the test world yet, or I mean, you're deploying it. I mean, it's certainly what the software engineers have been using to abstract out the rest of the stack of the server and the other software there. But what are the containers, languages people are using? I mean, how much flexibility do they have in what they, either a customer or a solution provider has in terms of containers to live on your platform?
Thank you. That's a great question. I would say by far Python seems to be the most popular language that people want to use to develop applications. It seems like it's the language of choice for AI and ML type things in general. There are other alternatives such as R, stuff like that. We have one customer that's using MATLAB, and in their case, what they're really excited about is the whole portability question. So they develop their MATLAB application on a Windows-based PC type environment, but then they want to take that piece of code, and normally what they'd have to do to run it on the ATE is they have to, refactor it. They have to recode it in the tester native language. And now they no longer have to do that. They just drop it in a Docker container and they can immediately run it on the application. If they're changing that MATLAB code over time because they're adapting and tuning their solution, it's very easy to just to respin the container and be able to reuse it. So there are a multiplicity of languages, and pretty much anything that you want to do, you can run it inside of a Docker container. So you really are almost limitless in terms of what you can do there. But Python is the choice that we see the most people making.
Mm-hmm. And in general, I mean, what is the advantage? I mean, I think you touched on it, but using containers, yeah, specifically for AI and machine learning, and might we see more containers used elsewhere in test?
Yeah, portability is a big one, and I just talked about that. One customer in particular is really excited about that, being able to move code around easily. Resilience is another thing. Normally when you deploy a new piece of test code, you're dependent on the state of the test cell in terms of what revisions of the OS are installed, what revisions of the tester environment are installed, what libraries do they have available on the tester. That may be one thing that you can control well if you're in an IDM. And you have complete control over those operations. But if you're a fabless type company and you use manufacturing partners, then you have less control over that. So, and then that can cause operations, things can go down, they respin an OS, and then all of a sudden you're no longer compatible with that environment. So giving you the resiliency to be able to depend on your applications running, regardless of what libraries and dependencies you built into your application, and that they're going to work because you carry along all those dependencies inside the container. That's a pretty attractive kind of technology, and I think that'll make people want to move to this technology more and more.
Mm-hmm. But on the flip side, I mean, looking at that architecture, you've got what I call a lot of black boxes with a lot of encryption and security. So, when it works, I'm sure it works flawlessly. But when you got to go debug it and try to make it work, I mean, is there enough observability and controllability so you know why it's doing what it's doing?
That's a great question, and we wrestle with that because on the one hand, we need a certain amount of access and we have to negotiate that access to make sure that we have it to be able to see things. And the other part of it is that, we need to put in the right monitoring features, and we're spending a lot of time thinking about what all signals do we need to monitor coming off the test cell to make sure the application deployed correctly, at the data that needs to come into the cell, say if you're feeding forward data from another operation, that it's there and it's present and it's ready to go and it's not corrupted. that the program initiated the container and was able to launch it appropriately, that the test cell is up, that the edge compute is up. So there's a lot of things that you need to keep an eye on. So yeah, it is a challenge, but we're definitely working on that. We have already some things in place and more ideas coming to make sure that we appropriately monitor and control the operation so that it's resilient and reliable.
Great. Okay. And then you touched on the ChatGPT, terms of training large language models. I'm assuming, but you can probably elaborate a little bit more about what's it take to train for code specifically. And I assume that there's some type of hybrid between using an existing LLM and then you add on your own knowledge base, or how are people tackling that?
That's pretty much what you said. You have to, if you've been doing this business for a while, you probably have a library of code that you do that executes various tests. So you need to make that code available to any and for training purposes. Some things are simple. Maybe there's not a whole lot of variation in how people run a continuity test. But Keith's more complex example like ACPR or things that you do in the analog space, in particular RF type technology, where perhaps there's some variations on the theme on how you can do it efficiently and fast. Again, you've probably spent some time developing that technology. You don't necessarily want to let that out, so you have to train it, within the confines of a firewall, and then make use of that when others are kind of going off and developing new test programs based on your content that you've created over time. So it's really about kind of cordoning that off so you have the right libraries and programs to train on, and then make use of that. Allow people to use that without necessarily making that open for the rest of the world.
I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.